Okay, so this is the solution guide for question 3 in tutorial 9. Let's read the question first. A feed mixture weighing 200 kg of unknown composition containing water, acetic acid and isopropyl ether is contacted in a single stage with 280 kg of a mixture containing 40% acetic acid, 10% water and 50% isopropyl ether. The resulting raffinate layer weighs 320 kg and contains 29.5% acetic acid, 66.5% water and 4% isopropyl ether. So in this question, you are asked to determine the original composition of the feed mixture and the composition of the resulting extract layer. So the equilibrium data given is the same as for the whole tutorial 9 because it's the same components and at the same conditions. So as usual, you need to plot the LLE curve using the given equilibrium data. So I just want to show you that you can plot the LLE curve in two ways. So one way is to have the A component in the x-axis and the C component in the y-axis, or you can also invert the axis where you put the C components in the x-axis and the A component in the y-axis. So you will get different shapes, different forms of the LLE, but essentially the data are the same, and you just need to know where to read the raffinate and extract layer. So if in the first diagram here, the first diagram, the blue line corresponds to the raffinate layer and the red line corresponds to the extract layer. And in the second diagram, in the right hand side diagram, here the red line is the extract layer and the blue line is the raffinate layer. So you need to know, doesn't matter how you plot the graph or how the graph is given to you, let's say in the question or in the real working world or whatever. So you just need to know how to read the composition and how to locate where is the extract and where is the raffinate and where is the tie line. Okay. So for the question, let's visualize the problem. So you have a single stage equilibrium process. So you have this L0 coming in here, 200 kg of initial mixture. You don't know this initial composition. You don't know the XA0 and the XC0. And you have the solvent coming in, V2 equals to 280 kg. And the composition of the solvent, YA at 2 is 0.4. So this is not a pure solvent. You still have some solute in the solvent. YC2 is equal to 0.5. And then the resulting raffinate layer, L1, is weighing 320 kg with the composition XA1 equals to 0.295 and XC1 equals to 0.04. And then your resulting extract layer V1, you don't know the amount and you don't know the composition. These are the things that you need to find. Okay, these are the things that you don't know. So first of all, let's do overall balance where L0 plus V2 equals to V1 plus L1 equals to M. So equals to 480. So 200 plus V2 is 280 equals to V1 plus 320. So you can find out what is V1. V1 equals to 160 kg. So this one is solved. So next we want to find XA0, XC0, YA1 and YC1. Okay, so now you have the equilibrium data as shown in the graph. So you can plot the known compositions. So let's plot the L1, the known composition. So L1 is the coordinate is 0.295 and 0.04. So let's do that. So let's plot the L1 point 0.0295, which is very close to 0.03 and 0.04 for XC. So this is your coordinate for L1. And then yeah, okay, wait. So L1 is in equilibrium with V1. So if you can plot a tie line crossing L1, so you can get the composition of V1. So from this L1, you try to approximate a tie line based on the slope of the tie line nearby in the middle. So just try to plot this line. Okay. So that is your L1. If you try to plot the tie line crossing L1, so you get V1 here. So from here, you can read the composition of V1. From here, you can get YA1 and YC1. So let's read the composition. So YA1 equals to about 0.14. Okay, this is what you are supposed to get if you do the plotting correctly. Mine may have a little bit of error because I'm using computer and the plotting is not so smooth. So, but these are the numbers that you should get if you plot correctly. And YC1 should be around 0.81. So ideally, the point is, wait, let me erase this. It should be here. 0.14 and 0.81. Okay, gives you V1. I'm trying to plot the line. I'm trying to draw the line here. Bear with me. Okay, not so straight, but you should get better. So if you have YA1 and YC1, then you can get YB1 if you want to have the complete composition of the extract layer. So YB1 is 1 minus YA1 and YC1, so you get around 0.05. Okay, so this one is done. So B1 done, YA1 and YC1 is done. So now you want to get what is the original composition of the feed mixture, what is XA0 and what is XC0. Okay, so to do that, we need to do a simple material balance calculation. So let me erase this. So just pretend like we are in the class where I'm erasing the whiteboard. So I'm doing that now while you are digesting what I've just said or shown you in the solution just now. Although you can just practically pause the video if you want to. Alright, so let's calculate the mixture composition. So XAM equals to L1 XA1 plus B1 YA1 over L1 plus B1. Okay, so that will give you L1 is 320, XA1 is 0.295 plus B1 is 160 just now, and YA1 is 0.14 divided by 480 as the mixture, so you get XAM. The composition of A in the mixture is 0.243, and then you also need the composition of C in the mixture. XCM equals to L1 XC1 plus B1 YC1 divided by L1 plus B1. So key in the numbers. 320 times 0.04 plus 160 times 0.81 divided by 480. So you get XCM equals to 0.297. But it's difficult to plot the points on the graph with 3 decimal places, so you can approximate this to be about 0.3 and this one about 0.24. Okay, so you plot the point M on the graph. Okay, so let's do that. So here 0.24 is about this way, and then 0.3, you stop at 0.3. So here, so this is your point M. I'm sorry, where did it go? Okay, this is your point M. And then, yeah, so what do we do next? So you know that M must be in between the lines of L1 and V1, and M is also must be, I mean, L1, M, and V1 in the same line. And also L0, M, and V2 also same line. So you can refer back to the lecture notes. So here we got point M. So if we know point V2, and if we connect point M and point V2, we can get the point L0. So let's do that. So V2, we can plot the coordinates of V2 because we know the points 0.4 and 0.5 for components A and C respectively. So let's do that. So 0.4 for component A and 0.5 for component C. So that will give us somewhere here. This is our point V2. So we connect the points M and V2. And then we get the point L0. So how do you get the point L0? Where do you stop the point L0? So here you have connected the point V2 and M to go all the way to find L0. So our best guess is to read the L0 where it touches the equilibrium line, the blue line. So from this point here, you can read XA0 equals to about 0.03 and XC0 equals to about 0.02. Well, points to ponder, and you can try this on your own. Can you get XA0 and XC0 by material balance? If you've already calculated the XAM and XCM, can you get the same value here using material balance? So yeah, please find out on your own. So that's all for tutorial 9 solution guide. Thank you.